Hello everyone. Our approach to detect out-of-distribution images using binary activation patterns is as follows. First, for all the training samples, we need to propagate them through the network and extract the binary activation patterns for those samples and memorize them into some data structure. Then, to check whether a test sample is in or out of distribution, we need to propagate it through the network and extract the binary activation patterns exactly the same way as we did for the training samples. Then we need to calculate the Hamming distance between the test sample and the most similar training pattern out of all those memorized, and based on how big the Hamming distance is, we can decide whether the test sample is in or out of distribution. So now a couple of important details about our approach. The first thing is that our algorithm is mainly designed for convolutional neural networks that use ReLU as the activation function. That's because the ReLU function allows us to easily represent the activations in a form of binary patterns. The second thing is that we can extract the binary patterns from every convolutional and linear layer. For instance, in this picture we've got a VGG16 architecture with 16 layers, so apart from the last one, we can extract patterns from every 15 layers remaining. The third thing is that we want our approach to be memory and time efficient, so we divide the extracted patterns, training patterns, into separate data structures by layer index and the label of the training image. So for instance, if we've got a data set that has 10 classes and we've got 15 layers to extract patterns from, we need to create a total of 150 data structures. This may seem complicated, but in fact it highly speeds up the process of finding the most similar pattern to the test pattern. So during the test phase, we need to classify a test sample and extract binary patterns from multiple layers. And then for each test pattern, we need to compute the Hamming distance between the pattern and the most similar training pattern extracted from the same layer. And also we need to remember that we limit ourselves only to those training patterns that were extracted from images of the same class that the predicted label of the test sample. And then we need to combine the multiple Hamming distances into a single uncertainty score. Be aware that not every layer have to contribute to the final uncertainty score. You can select those layers, for example, by a grid search using a validation out-of-distribution dataset. Now I should tell more about extraction of patterns, especially our technique to transform three-dimensional convolutional layer output into one-dimensional binary activation vectors. To do so, we split the matrices channel-wise and pool those channels independently. By pooling, I mean either computing an average value of the channel or the maximum value of the channel. Once we pool those channels and we represent each channel with just one value, we need to concatenate those values into a vector of length equal to the number of channels. And finally, we need to binarize the vector. And the binarization itself also requires a couple of steps. First, we need to zero a certain percent of the smallest values of the vector. For instance, if we choose the p parameter to be 50, then we need to zero all the values that are below the median value of the vector. And then we replace all the remaining positive values with ones. And finally, we can cast the binary representation of the activation into some memory efficient data type. We've evaluated our method in a very comprehensive way. We integrated 8 state-of-the-art OOD detectors with an existing benchmark called OD test, where each of the method is compared on 308 different dataset scenarios, where each scenario is a triplet of datasets. Specifically, there's one source training dataset on which the classifier is trained, and there are 2 OOD datasets. One is used for training the out-of-distribution detector, and the second one is used for an actual evaluation of the detector, so that we avoid unwanted situations where an OOD detector only knows how to separate one particular OOD dataset. The final results show that our method is very effective. It outperforms every other method on both architectures and quality metrics, but what's also important, it's quite fast, because we need only about 10 milliseconds to fully process one test sample. So a quick recap, we introduced a novel auto-distribution detector that uses an internal knowledge of classifier about images which we form into binary activation patterns. And as a byproduct of our work, we also publish the largest existing benchmark for out-of-distribution methods, which now consists a total of 18 out-of-distribution methods. That's all. Thank you very much.